this video, I'm going to introduce you to some goal programming. For that purpose, we look at why where we can use goal programming for, and then we look at two solution methods. One is the weights method, and the other one is the preemptive method. So what we have seen so far is that we had an objective function that had some goal. Mostly it was, or either it was minimization of costs or it was maximization of some kind of profit. Now I'm going to introduce to you the field where we have no solution space given, because there are constraints that are made in a way that there is no solution space. So with a given problem, we cannot find a solution if we don't violate one of the restrictions that we have given. So the goal programming method introduces some kind of flexibility to the problem, where if necessary, there can be a violation of one constraint. So you will find the goal programming method also in the field of multi-objective decision making, or also called multi-attribute decision making. So they pertain to the same field, and they abstract from stochasticity. So we assume here that we have a deterministic problem that is certain with the given data that we have. So as said, we have two methods here available that we will look at, the weights method and the preemptive method. So for the weights method, we define a single objective function with some terms, where the terms of the objective function are a weighted sum of the goals that are pursued, and the weights then they represent the kind of prioritization of those goals. So we have n goals given from index e to n, and in that case here we minimize some objective function where the weights here are defined by the decision maker. So here we are also in the field of subjective decision making, because the decision maker has to define his or her weights. So how much it hurts if a certain goal is not pursued, or which goal should be pursued first. So let's concentrate on the example here that we have given. It is an advertising company called Leon Burnett that has to determine the TV advertising schedule for a customer. This customer has three goals given here, and now the advertising company should purchase two types of advertising for this customer. They should be shown either in football games or during soap operas as a break. And the customer has at most $600,000 available that he can spend or she can spend on the ads. So now, they want to reach a certain potential audience, and we have also given some more data in the table that follows. And now the company should determine how much minutes to purchase and during which type of program in the TV. So, the linear program of the problem can be formalized as follows. We have, in this case here, it is given that we minimize the costs, so that we spend at least, or at most, some budget with respect to the number of minutes of advertisement shown during the football games or during the soap operas, with respect to some constraints. Here, the first constraint that we have seen, that for high income, we want to reach high income men, at least 40,000. low-income people at least 60,000 and high-income women at least 35,000, with respect to some coefficients for the number of minutes during football games and soap operas that we will see in the table later on. And here's the budget constraint that we have given. By the way, the objective can also be formulated as the maximization of the number of people that we reach with the advertisements. Now we have it here as a cost or budget minimization problem, but it doesn't matter. If we look to the graphical problem of this formulation, we can see that when we look at the budget constraint, that we could reach just the goal for the high-income women, because here we have a cross point of these two. But if you look at the others, then you will realize that with this budget constraint, we cannot reach as many low-income people or high-income men that this customer would like to. So it's impossible to satisfy his goals fully. And now we need to find out how much this customer is going to give up some of the goals by how much to introduce this flexibility that we need in order to find a feasible solution. Because as you can see here, the budget constraint is limiting our solution space to this area. The high-income woman, this constraint, we want to maximize the number of people that, or the number of high-income women that we want to reach, and this goes outwards. So this would be fine here at the cross point, but with respect to the other people that we want to reach, there is no solution space. So we need to introduce the flexibility that we can do with goal programming. Here is the table where we find the coefficients for x1 and x2, and also with respect to the constraints that we have seen. And now or the Burnett company is asking his customer how much it will hurt him to give up some of the goals. So for instance here, we have with respect to the high income man goal, a penalty of $200,000 due to lost sales, because we have not reached enough of this people with this characteristic. $100,000 penalty if we don't reach the low-income people, and $50,000 if we don't reach enough high-income women. The goal programming formulation that is also a linear program is now formulated as follows. So in this case, we want to minimize the penalty costs that the company encounters because the budget is limiting the solution space, let's say. So this is how it's formulated. These are the penalties with the weights together. And these are our constraints, where now we introduce some deviation variables, where, for instance, here, or the S in general, the S plus, denotes the amount by which we exceed the ETH goal in this case. So here, if we do not meet the goal, or if we are under limiting or undermining the goal, then we have this minus here. And if we exceeding this goal, then we have the plus here. And this is why we can now write also the equal sign here with respect to this goal. So here, this is the flexibility that we introduce for each and every constraint. And as you can see here, also for the budget constraint, we don't introduce a goal, because that is the budget that the company wants to spend, and not anymore. You have seen also in the other video that was given how to implement this problem in Excel. So you can set up the table where you have the standard variables with respect to x1 and x2 and the coefficients together with the constraints. And then the introduction of the deviational variables for each and every constraint. There you have the sum of the left-hand side, then summing up and the right-hand side, as we know it also from other linear programs. And this calculates then the deviation together, and that is an extra information. Now you might want to introduce some lower bounds with respect to all the variables. In this case, we haven't introduced any of these, and here in yellow you find the decision variables. The objective coefficients, and this is interesting now, are given here. So we introduced it for all the deviational variables, but because the customer has penalties just for not reaching enough of these certain people, for instance, the high-income men, or the low-income woman, the low-income people, and the high-income woman here, we just introduce these three together. And the objective is minimization of the overall costs. So here you can see already the optimal solution, and this shows us here that the minutes that we need to spend. So yeah, I don't want to be now too precise on this, but I want to give or to draw your attention to the D3 minus penalty here. And that means that the goal 3, if we look or if we perform this schedule with this amount of advertisement, then we don't reach enough of the high-income woman as previously wished by the customer. Okay, so for this video, the focus is on how to implement this in AMPL, and this is what I'm going to show you right now. I prefer to have the mathematical statement in front of the eyes, so I'm using to have this one. I show it to you from scratch, so we are creating a model file. I'll call that Goal Programming version 0. And yeah, the first thing now that we want to do is we introduce our variables. We have them also given here in the list. So yeah, normally we started on having the parameters first. So maybe I just keep it as we always do. So we first define the parameters, and for the parameters now we need to have the penalties, so the weights. So we have for the first penalty we want to give, or the customer gives the value of $200,000. So this is penalty for x1 and the limit. Then we have for the second constraint not meeting low-income people, or the right amount of low-income people, we have a penalty given of, or the customer gives it of 100,000. So this is for the constraint 2, or for the goal 2. And then we have the penalty for not meeting enough high-income women. So the next thing, I think that were all the parameters, yeah. Because in this video I'm going to deviate a little bit from the standards that we define or that we divide the model from the data. I put it all in the in the statement for the model. You can always do it, it's just not that elegant, but in this case I'm deviating a little bit from our standards. So the next thing that we want to introduce is, so these ones, the weights we have already given, and now we want to introduce the variables. So we have x1, and we define it larger or equal to 0. We can copy that as we will use it a lot. And this was the variable for the football game. Then we introduce x2 with the same setting. And these were for soap operas. For the soap opera, it doesn't matter. And then, so these were the two decision variables. And now we introduce the derivational variables. So we have S1 minus. That is also larger or equal to 0. And then we go on like this. So we have S1 plus larger or equal to 0. These are these two now, and now we need 4 more. So we have S2 minus S2 plus S3 minus and S3 plus. Now I'm checking. So these were the derivational variables, and this is all that we read right now with respect to the parameters and variables. And now I already introduced the mathematical model, beginning from the objective function. So we minimize a function that we call zeta. And this is composed now, as we can see in our mathematical model, by the weights for underscoring our goals. So we have, for the first one, S1 penalty multiplied by the derivational variable S1 minus, plus now the undermining the score for the low income people. So this is S2 penalty multiplied by S2 minus, plus now the S3 penalty multiplied by S3 minus. And we finish with a semicolon. Now we have some constraints. So we have subject 2. First constraint, C1. And as I said, now we introduce the coefficients directly in the model. That is not very much elegant, but it shortens a little bit things. So this is our first constraint that we need to plug in. So it's 7 multiplied by x1 plus 3 multiplied by x2. Oops. And now plus S1 minus and minus S1 plus, and this should be larger or equal to 40. So that was the goal of the high income men. Then we have the second constraint. That is now 10x1 plus 5x2, and the derivational variables. So it's 10 multiplied by x1 and 5 multiplied by x2. Now I'm speeding up a bit. So we copy from the other constraint, they are similar. So we spare a little bit of typing. So the derivational variables for the second constraint, and we want to have it larger or equal to 60. That is the goal of reaching low-income people. And the third constraint, also given here, is 5x plus 4x2. So 5 multiplied by x1 plus it was 4 multiplied by x2, and the derivational variables for the third constraint, and this should be larger or equal to the 34,000 of high-income women that we want to reach. And the fourth constraint is the budget constraint, given as follows: 100 x1, 60 x2 is smaller or equal to 600. So 100 x1 plus 60 multiplied by x2. And now we don't introduce deviational variables because we want to reach the goal of not spending at most 600,000. So that's the budget constraint. Yeah, as you can see, that is the whole mathematical model that we need to state so far. Now I put together also the run file, so you can put the whole model together with the data together in the model file. So I write run file, as long as it works, it's fine. So we use option solver Cplex to solve the model. We define our solve command. And now for the solution, we want to have displayed the objective function value at first. Then I would like to see x1 and x2. And I also want to see the derivational variables for our constraints. So I take the S1 minus together with the S1 plus. Now we can speed up again by copy-pasting. I want this for all three constraints that are not the budget. That is not the budget constraint, because that one I want to not derive from. Okay, so far so good. Let's see if I made some typo. So this is GP0 mod, and because we have thrown everything now in the model file, we can just invoke the model file and it should work or not work. Now you see that I made some mistake here, and that is in line 37. Okay, and in fact I did something wrong in line not just 37, but in all of them, because I typed semicolon and I want to have a simple comma here at that stage. Here it's fine, but here I made the mistake. So let's reset. And you can see that we get the right solution. Objective function is 250, and we buy for that company 6 of x1 and nothing of x2. And we see here also that with respect to the third constraint that we have a derivation in underscoring to meet the high income women. So this is how you can implement the model in AMPL. And to check again here, we get the same solution as for the Excel version, of course, because it's optimal. And now I want to draw your attention to some modification. What if now we say that we can violate the budget constraint, and now we introduce a penalty of $1 for each time or for each amount of where the goal is unmet. So we introduce derivational variables now also for the budget constraint that you can see here for D4 plus and D4 minus. And now we want to do this also for the AMPL version of our model. So we take the same file and I save it as GP1. How to consider this modification in AMPL? We introduce the derivational variables for exceeding the budget constraint, or underscoring or overscoring it. So we introduce the S4 minus larger or equal to 0 and the S4 plus as well. And so we have the two variables given. Now we introduce the penalty of $1 additional if we exceed this. So if the derivational variable S4 plus is exceeded, and I don't introduce a penalty coefficient here because we said it's $1, so I don't need to add that here. But if you want to make it more flexible and you want to divide the data from the model, then you should also introduce a parameter for the S4 penalty. Next thing is we'll need to look at our constraints. So now we have a modification in the C4 in our budget constraint, where we introduce now the derivational variables. We need some space. So we introduce S4 minus and S4 plus. And the rest stays the same. Well, not exactly, because I want also to have the display now for the S4 minus and S4 plus. So we add that also to our display function. It's our display. And that should be all with respect to the modification. So we reset AMPL and we invoke the model GP1 now. And now we get the new optimal solution. We have an objective of 33.3 period. And now we have also different purchasing amounts for the advertisements. And we see that now we exceed, in fact, the budget constraint with this solution.